Okay.
All right, we are going to move to the next section of materials. So we have transistors in this section, and then we're going to talk about RLC, which is moving towards second order solutions for circuits. So lots of fun. So transistor is a very useful device. So today our goals are going to be to identify a PNP versus a PNP. These are BJT transistors. So there's two types of transistors, a BJT transistor and a MOSFET transistor. You're going to understand, or the goal is to understand that there are three modes of operation for this type of device. You have an on stage, an off stage, and on the on stage, so off is cut off, and then on is going to be either in active mode or in a saturated mode. So for being on, you actually have two conditions. Another goal is to understand the direction of the flow between an NPN and a PNP, and then understanding the steps to solve a circuit when you have a BJT transistor in there. Yes? So this is a BJT. So it has three connections to it. So you have a connector there, a connector here, and a connection here. This is called your collector. This one is called your base, and this one is called your emitter. So this is a NPN BJT. So three connections to it, a collector side, base, and emitter. The emitter side is the one with the arrow. And so that's how you know which orientation it has on it. So three different connections. How this works is that the diode was a PN type of junction where it had P for positive and for negatives. You had different charges and you put them together. So that is a P and an N. So here you can see between the base and the emitter, you have that PN junction there. So that's where that little arrow ends up kind of looking like that diode, because it is internally like you have a connection of a diode between your base and your emitter. So when this is on, we use that diode and say that this has a 0.7 volt drop. So this is where that diode understanding comes in. So what happens here is your base is like a faucet. When you turn it on, you get to a point where the faucet starts running water, and the water flows through the pipes and through the faucet. So that is really what happens, is that your base is the controller, and then you have flow of current from IC that goes through to IE. So most of the applications you guys are going to look at will probably be a switch application, where once it's on, it's going to switch the current to flow from your collector to your emitter. So that is the most common way of using this for you guys. They're used also like in digital logic, where you're turning them on or off, and then you can use them actually as an amplifier and create kind of like an op amp from them too. So we're not going to go into a ton of depth with looking at them for different applications. What I expect from you guys is just to look at them mostly to hook up a motor, so you want to turn the motor on or off. And so a lot of times you're going to hook these up to a microprocessor, and they'll act like a switch basically. To go to your motor, sorry. So this is your motor. And out of the microprocessor, sometimes you need like 1 amp, sometimes even 12 volts to turn on your motor. And out of a microprocessor, you usually get like just 5 volts, and then you can get like 20 milli to 40 milliamps from there. So you usually don't have enough from a microcontroller. Sorry, this wasn't as clear. So a motor may need like up to 1 amp, maybe 12 volts, where like a microcontroller, Arduino, may only give you like 5 volts and 20 to 40 milliamps. So one way to do that is just to use this switch to then have a different power supply that will turn it on once you have that control signal from the Arduino into the base of a BJT, and it will say like, yeah, turn it on or off. And so that's the most common application. So use, sorry, BJT. So this is the most useful thing for the BJT for most of you guys as mechanical engineers. So this would look like you would hook it up to the 12 volts you need. You would hook up your motor here. And then you would just hook it directly to the top of the BJT. And this could then be just grounded. And then you would hook your Arduino to the base of this one. This R would then be used to control how much current is going to then the motor. And we'll talk about how you get that control in a minute. And that's how this one works, is that once you have the right amount here of voltage, then your current flows from this collector side IC to your emitter side IE. So that can give you, if you need 1 amp, that can give you up to 1 amp there. All right, questions on kind of how and why you're even wanting to look at these? So I'll just say this acts as switch, kind of on off. All right, so as I said, you have the 3 components, a collector, a base, and an emitter. This is your NPN. Your current is going to flow from your collector side to the emitter side. How do you know which side's the emitter? Okay, so the little arrow on this one. So that's how you know it's the emitter side, is the arrow on the BJT. So here you see that the arrow's actually at the top and going in. So that side will be your emitter side. And this will be a PNP. The collector will be on the bottom and your base will still be over on that side. Here your current flows from the emitter side, it goes down to the collector and then out the base this way. And here your base current goes in. So they have a little bit different flow of how the currents go in and out. All right, so cutoff is when your base, so you're going to start seeing, it's called two subscripts. So VBE is going to be a common one. This means it's the base minus the voltage at the emitter. So whenever you see two subscripts, that is always just the first one minus the second one. So in this case, that means the voltage at B minus the voltage at E, that difference, if it's less than 0.7, it's going to be off. If it's off, then there's no current flow. So IC equals IB equals IE, and they're all going to be 0. So that's your off condition, which is easy. The on is a little bit harder, where you have a little bit different conditions. So for on, that means that VBE is going to equal 0.7 volts for both your on stages. So for an active, this is going to be that VC is greater than VB for an MPN. It's going to be opposite for a PNP. In the active mode, we can use a condition that these are related by what's called beta. So if we're in active mode, we can use this relationship. There's another variable called beta, and then there's this alpha. Alpha is beta over beta plus 1. So what this beta is actually internally, it's how much of the doping of, meaning the plus charges and the negative charges that are in there. So it will vary anywhere from, so beta can be anywhere from 40 to 400. And so it has a very wide variability based on how this particular transistor was made. So what we're going to do is pick a typical value that's used for hand analysis, and then usually what you do is take it to a simulator, you build it, you'll measure what beta actually is, and then you may have to go from there as far as your design. There are ways to try to design it to make it not sensitive on beta, so even if you put a 40 in there, it works the same as if you put a 400 one in there. Again, we're not going to go into as much depth in here as that one, but do want to just have you guys be aware of that. All right, for saturation digital, which is just where it's fully on, which is mostly the stage you guys are going to look at, you can no longer use this relationship. So instead, you know that the current summation for an NPN, do it in blue too. So I'll put here use, and then in this one, you're going to use for an NPN that IB plus IC equals IE. And for a PNP, it will be, actually it's the same. IE goes in, and then it goes out the other way. So those are actually the same. The other thing that you're going to use is a VCE value. It's usually 0.2 to 0.7 volts. A lot of times on a data sheet, you'll be given a range of a typical value, a minimum value, and a maximum value. So typically you would just use the typical value and again, design it, go take it to a simulator, then go build it, and then actually make modifications knowing that these are going to be actually a little bit different. All right, questions about this? Okay. One other check. So here the check for the state is if your voltage at your collector is greater than your voltage at your base for NPN. The check for a saturation and digital is that beta forced is a lot less than your normal beta. And beta forced is going to be your saturated current for your collector over your saturated current for your base that you find. So you just find those values and find that beta forced. And as long as it's a lot lower, like say beta you think is typically around 100, and if you find beta forced to be 1, then you're like, yes, I'm definitely in saturation. All right, so solving a circuit with voltage and currents with the BJT in it now. So you're going to assume either active or saturation mode. So basically assume first it's on. You're going to put the base to emitter at 0.7, so you're going to just make that assumption that it's got 0.7 volts there. You're going to then solve for the BJT nodes and voltages. In active mode, you're going to use that relationship of IC is equal to beta IB is equal to alpha IE. And you're going to take, for either mode, you're going to take a loop equation from the base to the emitter. So this is because you know the voltage between the base and the emitter. So that has mostly the known information. So you're going to take a loop through there. And then once you find IB or IE, you relate it to IC. If you are in saturation, instead of taking, so this is active. If you're in saturation, you're going to use instead that IB plus IC equals IE, and VCE is approximately 0.3 or 0.2 are usually the most common ones to use. So using these two instead. If you solve them and then you find that VC is greater than or equal to VB, then you say that NPN is active if you assumed active first. If not, you're going to check the IC for saturation. You're going to find IC sat and then IB sat and make sure that that is a lot less than beta. That would be your check. All right, you guys ready to jump into some solving? Sure, okay. All right, so here we have a circuit with a BJT in it. We're gonna make first an assumption. So since the switch is open here, I'm gonna assume that this is off. What does off mean? What are the currents for off? So it means that all of these are 0. So that means 0 here in the current. If I have 0 current, so 0 amps. If I have 0 current, what is VC? Volts, correct. 12 volts. And IB will be 0 also. And so if you have 0 volts here, what's VBE? Which is your base voltage minus your emitter voltage. What is VE? 0. So VBE is 0 volts, which is less than 0.7, so therefore it is off. So this is your check for when you assume it's off. Okay, not too hard, just looks a little scary. Okay. All right, looking at power is going to be something that you guys have to be more considerate of with the motors, because the motors will have a very specific limit of how much power they can take across them. So in this case, what is the power? So again, this is 0, 12, and 0. Your power at the BJT. So the BJT will blow up at a specific power, so you don't want to have too much power going through the BJT. So there are BJTs that are rated for higher wattage, which you would want to use for motors in particular. So you got to make sure you use the right BJT, otherwise you may blow them up. So this power is going to be your VCE, which is the voltage between your collector and the voltage between the emitter. What's your emitter here again? 0, thank you. And so you have 12 volts across that. But IC is 0 in this case, so there's not going to be any power draw here. But if you put 12 times 0. So in this one, I should say approximately here. So the consumption, though, is that you actually have both of the VCE times IC, and you also have a VBE times IB. So you're going to be needing to consider both. IB is usually really small in comparison to IC, so we can usually just approximate it by the voltage drop across VC times that IC. All right, so let's close the switch now. So this was the easy example. Now we want to close the switch. We're going to assume that beta is 100 is an easy number usually to divide and multiply by. So we usually use that for hand analysis. When we shut this switch now, or we have the voltage from the Arduino of that 5 volts, we now have current that goes in here of IB. We have the IC going down, and then IE will actually be here, but since VE is 0, so with it being partially on, we're going to say this is active mode. So we're going to assume active. With that, we can set VBE equals 0.7, and then we also can use this relationship using beta. So IC is equal to beta IB is equal to beta over beta plus 1 IE. Our check here will be if VC is greater than VB. So that will be the check that we'll need to do at the end. First step is to always take loop from base to emitter. And that is because we can set this voltage between here and here as 0.7 volts. Here we don't know what VC is, and we know what VE is, so VCE will be VC value, but we don't have a value for that one yet. So we do know all the values through here though. So going from ground to 5 volts. So our loop is going to be plus 5. I'll go through and circle these. So plus 5 plus IB times RB, and then a minus 0.7, and that gets us from ground back to ground. So 5 plus IB times 5K minus 0.7 equals 0. So IB is 4.3 divided by 5K, which is 0.86 milliamps. Yeah.
Why is IB being added? Why do we have the positive convention on the
Sorry.
numbers on
No, one of my days that it is negative. Sorry. Thank you. Negative, positive. I'm being dyslexic today. Okay, minus, so then IB goes over to the other side, 4.3 over 5K. Yes?
If EE is 0, why are we subtracting %? Like, why is it?
So there is a voltage here, VB,
Oh.
and there is a diode, like internally there's a diode in there. And there's also internally a diode between VC and VE, but it's kind of think about it as like some component in there. It doesn't act like a normal diode. So we can't say it's easily like just 0.7 volts across there. It's actually only like 0.2 or 0.3 when it's fully saturated, but it varies internally based on how much current is coming in. So it's an unknown value between VCE. But with VBE, we know that once it's on, it acts like a diode, and we know that voltage drop between there.
Okay, I see.
So we have to use that known voltage drop to help us solve the circuit there. Does that make more sense?
Yeah. Oh, yeah.
Okay. All right, other questions? Okay, so now we have IB, we can find IC by that relationship. So we say IC is equal to beta IB, which beta was given as 100.86 milli. So IC is 86 milliamps. So now to find VC, what is my equation to find VC here? Anyone? Go for it.
64 minus 86, 700.
Thank you.
Or 86 minus.
Yep. So you just take 12 minus the drop across the RC, which is 86 milli times 100. And so this ends up being 22, wait, no, wrong one. Where's VC? 3.4 volts. There we go. VB is 0.7 volts because we set it to be that value. So is this active and on? Yes, or question first.
When you did your loop to find IB, the 5 was actually from VBB, correct?
Yeah.
And so the loop was VBB and then V. Like what path is the loop, I guess? Is the question.
So I went from ground through there, through the emitter side back to ground.
Oh, it's just
Yeah, it's just that bottom portion. Also know, like if you set 0.7 and your VE is 0, then your VB, hopefully you can just see right away, well that's 0.7. I could also write this using just Ohm's law for IB. IB is the right or the left side, which is 5 minus 0.7 over 5K.
that's the 0.7 because there's a diode built in.
Correct. Yep, because that's the characteristic of the BJT. So you have to, that's one thing to know as far as a concept wise, like yes, internally there's a diode when it's on between the base and the emitter, and it acts like a normal diode of 0.7 volts drop. But we also know there's some current that flows there, and then we don't know there's a variable kind of diode in between the collector and the emitter. So that's an unknown voltage because it varies over how much current comes in. So we don't know that until it's fully on and in saturated mode when it becomes fixed at like 0.2 or 0.3 volt drop across that one diode. But it will vary in between there, so you don't know exactly what that one is. So it's hard to take a loop through the collector and the emitter when it's active on. We can only do that when it's known state of like, yes, you're fully on, it's not going to change anymore between the collector and the emitter. Does that make sense?
Yeah, thank you.
Uh-huh.
And then why were we able to say VE is equal to 0?
So it's grounded. So it's wired right to ground. So 0 volts. Any other questions? Okay, so power here now, we can make that approximation of just saying it's the voltage between, there we go. Voltage between the collector and the emitter times my IC collector. So 3.4 times 86 milli, and that ends up being 292.4 milliwatts. All right, so now we need to check and make sure it does meet the conditions for active on. So we check for VC, which is 3.4, which is greater than VB, which is 0.7. So yep, on and active. So sometimes you may check this and be like, well, it's on, but my base voltage is greater than my collector. So that would be where you would assume then it's in saturation and go through the methods of solving for saturation. So unlike the diode only has on or off. This one will have the 3 different modes. So you do need to make sure you're checking for each of those. All right, questions? Okay. So I wanted to just give an example of like how much difference can you see when you have a different beta. So this one, assuming that beta is 200, you get the same value, 86 milli here for IB. So IB again is just 5 minus 0.7 over 5K. You get 0.7 here, so you get 0.7 volts. So these are the same. What varies here now is that IC is going to be 100 times, or 200, sorry. 200 times 0.86 milli. And then this gives you a VC of 12 minus 0.172 milli. Yeah.
Shouldn't it just be 172? 200.
Yeah, 172, yes. I'm not doing too great today with the math. Okay, 172 milli. Times the 100, so you get, it's 0.172, but not 0.172 milli. So this ends up being a minus 5.2 volts. So you can see here, like, no, this is not then on and active. So for saturation, so it's not active in this case, and this is kind of showing that it's not, because you end up with VC, which is going to be less than 0.7 volts. So this is an example of like, oh, I made an assumption and it was incorrect. So now I'm going to reassume that it's in active this time. Or I mean in saturation this time. So for saturation, we know that we can use that VCE and I used 0.2 volts. And so this then fixes the voltage between here and here of 0.2 volts between VCE. So now I can take a loop from the VCC all the way to ground to find IC. So because that's ground at VE, then this becomes 0.2 volts here, and then I can use Ohm's law, or I can do a full loop. Ohm's law would be 12 minus 0.2 over 100, which gives me 118 milliamps. And my check on this is to check this IC sat over IB sat, which is 118 milli over 0.86 milli, which ends up being, I don't know what that is, 118.86, which is 137. Which is less than 200. So now the power, looking at the power consumption, VCE times IC, we have 0.2 times 118 milli, which is 23.6 milliwatts. So one takeaway from this is that saturation condition consumes a lot less power. So 23.6 milliwatts, same circuit with the same resistors. That one had 292 milliwatts. So a lot difference in power consumption. So this is good to know. Just if you are going to do this kind of setup for a motor, you want to use it and make sure it is driven in the saturation region instead of the other region, instead of active mode. So I mentioned earlier, this resistor here, RB, acts as kind of that control resistor. So if I change that, that's going to change my IB, which then will affect IC, and so on. So that's what's going to drive you if you're like, oh, I'm not quite in saturation mode. What would I want to do here? Increase or decrease RB? So decreasing RB will increase IB. And if I increase RB, I decrease IB. If I have a larger, well, VB will stay 0.7 either way. right? Because you fixed it with it being on. So VB stays 0.7. What is going to determine whether it's active or in saturation is your VC. So VC you want to make sure is less than VB. So if I lower IB and I have an active mode relationship, is VC higher or lower? What do you guys think? So if I've increased IB, what happens to IC? Does it go up or down? If I'm inactive, it would also increase, right? Because IC is beta IB. If I've increased IC, what happens to VC? Lower or higher? So 12 minus ICRC. So if I've increased IC, I'm going to have a larger drop, so VC goes down. So it will keep going down until I reach a stage where they're equal, and that will be the threshold in between that active and saturation. If I keep making it lower, it's going to move it more and more into that saturation. So this would be the condition of where if you first were like, oh, I'm drawing a lot of power, I want to actually reduce that by moving more into the saturation region, you would increase IB, which would be decreasing RB. So you would decrease it. Does that make sense? Okay. All right, so here's another example. You guys take a second to so first assume it's active. So assume active state and use beta is 100. Let me get a
I thought it worked out
Getting active IC is beta times IB.
Listen like this. None of the people in the stands who are
Times 10K
Yeah, so it's gonna be plus 20. And then a minus, so it's 20 minus our.
No, you know the current already.
You guys check the dial.
What do you mean, not current?
You know the IC, because
Yeah, so then to find OEC or.
yeah, but that's so many questions. That's like crazy number. Like one times the other. No, times A. Then you get like 100,000. So I'm starting to think it's not as active because what is it? It's that we're getting something from ECE is way greater than BB.
Yeah, so our ECE which I check.
She's trying to like go like yes. It's because researchers have what they say. It's
Our check is BC is greater than 0.7. Which it is.
This is a real time. That's for yeah.
What? That's for what? What is that?
VC could be less than VB if it's so we know it's we already know it's not because this is not so yeah, I don't know this VC because the emitter is down like this. The emitter is up here and going down. It's so if it's NEN, check which it's not. No, EC is right there. So it's just ungodly amount of things. Oh wait, no, it's not. It's negative 1,000. It's negative 1,000. So it's actually not active. It's saturated. And if it's saturated, it's IB plus ice.
I might be wrong.
What up, man? It's gonna be. What?
IB plus ice. The current IC. Which is, we know that the G100 is
All right, so looking at this with assuming that it's active, you're going to have that 0.7 volt drop there, which puts this voltage here at 3 minus 0.7 or 2.3 volts. So you can find IE right away by IE is going to be that 2.3 over 2.7 kilo ohm, which gives you 0.85 milli. Knowing that, we can then find IC, which is going to be 100 over 101 times 0.85 milli, which is, where did it go? Okay, 0.84. And then the voltage here is 20 minus 0.84 milli times 10K, which gives 11.6 volts.
The same lab.
So is this active and on? Is this active and on? Yes. Why? Correct. VC is greater than VB, so therefore it is on and active. Questions? Yes.
Where'd you get 100 over 100 going from?
That's alpha. So the relationship IC is either beta IB or it's alpha IE, where alpha is 100 or is beta over beta plus 1.
So wouldn't it be flipped and be 101 over 100? Because when you convert it, it'd be D plus cash over B times IC.
No, it'd still be, so IC is equal to alpha IE. So if you're trying to find IB, so IB would be IE over beta plus 1. Or IC is beta, which is 100 over 101 times 0.85 milli.
Is it a good assumption just beta
Yeah, you can just use beta as kind of 100 to start, if you don't know what beta is, to get a hand calculation for it. And then a simulator is going to do a better job than you will by hand. All right, so any questions on this? Okay, power. Power of the BJT is going to be VCE times IC, where VCE is 11.6 minus 2.3 times, where'd IC go? 0.84 milli. So that ends up being 0.6 minus 2.3. 7.8 milliwatts. Okay. Yes.
So is beta just like a property of the transistor, or is it?
Correct. Yep. So it's actually determined by how much the positive charge and the negative charge was put in the actual BJT in the different areas of it.
Okay.
So between that collector and emitter, it's what's called doping as far as that positive amount and the negative amount and the interactions that they have.
Okay.
So it does depend on how it was made, and that's why it varies greatly.
Yeah.
Between 40 to 400. So what they do is they usually make a huge batch at once. They'll make all of the transistors in one batch, and that whole batch might be around 40. And then they'll make another batch, and then it will be like all around 400, depending on how it was actually created.
Okay, thank you.
Yeah. All right, yes, other questions? So I did use the loop. I used the 0.7 where it's highlighted as yellow. So it's 3 minus 0.7 is 2.3.
Yeah, for DC, I was confused, is the voltage 0 at or
So VCE is the voltage at the collector minus the voltage at the emitter. And the voltage at the collector is 11.6, and the voltage at the emitter is 2.3.
okay.
Does that make more sense? Okay. So that's where I got that VCE from. So that is a voltage difference, which sometimes is hard to think about when you think about, okay, if I have two batteries, I'm actually taking the difference between the two batteries. And that's a difference, and that's when you see that labeling of like VCE, VBE. That's the difference in voltage between those two locations. It may not be an actual physical connection, and it may. It just depends. But most of the time, there'll be some element in between there. In the BJT case, you don't know what's really going on in between those two locations, but you know there is a variation in voltages at different times. All right, other questions? Yes.
So is it the VB that's the voltage going into the lower branch on the other side, like the yellow line?
So right
Are those
here
two, like, connected?
is this VB, is right here.
Yeah, but like you found the voltage right after that one diode, and you did 3 minus 0.7.
Uh-huh.
So then how come for the top diode you can do like the 20 volts minus 3 volts over the resistance?
So here to here would be VCB. That's usually not much useful information.
Oh, I was just saying to find VC, because like the 3 volts didn't change when you went down to try to find that.
Yeah, but you don't know, like, so to get from base to collector, you either have to go from base through that VCB, but you don't know what that drop is. It is some voltage drop, but you don't know what it is. It's not a known voltage internally.
Is there no voltage drop across the lower line? Like when you go from the 3 volts and then you did this subtracting 0.7?
So we know that this is fixed at 0.7 if it's on because it's acting like a normal diode.
Okay.
So that's why we can go through that route, because we know like, oh, that's like acting like a normal diode and that has a 0.7 volt drop to it.
Okay.
So that's why we take that loop. So it's not zero between there. It's not zero between any of the junctions. You just don't know what that voltage is. When it's on in either saturated or active, we know that there's that drop between the base and the emitter. And so we use that information to then find the other currents and voltages. Here we don't know. We don't know here between there, the base and the collector. And we don't know here until we found what the voltage at the collector is. And so we use those, they're called active mode relationships of IC equals beta IB equals alpha IC, IE, alpha IE, to get the current that then we can find VC. In saturation mode, we do know, we're assuming that we have this drop of 0.2 across here. With it being on, we also make the assumption for VBE equal to 0.7. So then we use that information to take the loop through VCE. Does that make more sense?
Okay. Yeah.
Yeah. Okay, great. All right, you guys want to try this one? So this is assuming it's in saturation now. And you're going to use this relationship instead. So the other thing in saturation is that you know that the current summations will actually sum to IC plus IB equals IE. All right, take a minute to try to solve this one, and then we'll go through a solution.
Joke's on you, my ears are gone.
All right, so you have three unknowns, IC, IB, IE here. So you're going to use equation 1. And then you're going to use a loop through the base to the emitter. So that's equation 2. And then you can take a loop from the collector side through to the emitter. This is equation 3. And then I would recommend a solver. So putting those in, if I put them in Wolfram Alpha correctly, 3 minus 10K. So Wolfram Alpha, if you do use it, don't use I as a variable in there. It looks at I as an imaginary number. So you want to just change the variables. So I just changed them to C, E, and B, meaning that's the currents in those. And this is what it ended up giving me for those. So 3 minus 10K times IC minus 0.2 minus IE times 1,000. And then IC plus IB equals IE. And then 2 minus 10,000 IB minus 0.7 minus 1,000 IE. So this yielded IB ended up being 1, 2, 3, 4, 5, 6, 95.8 microamps. IC was 1, 2, 3, 0.245 or 0.46 milliamps, and IE 1, 2, 3, 0.34 milliamps. So then we can find VE from IE times 1K. And that ends up being, what is that? 0.34 milli. So 0.34 volts. And VB then is 0.34 plus 0.7 for 1.07 volts. And VE is going to be 3 minus 10K times IC, or, sorry, this is VC, or VC is VE plus 0.2 for 0.54 volts. What is the check that we have to do for saturation? Anybody remember the check? Thank you. Yes, IC sat over IB sat. And then this is 0.246 milli over 95.8 micro, which gives us 2.57, which is a lot less than 100. So it is saturated. Yes.
Where did the 0.37 come from in VB? 3.34.
Point. So say that again, where?
Where did the 0.37 come from in 0.37?
No, I don't know. Thank you. Yes, 0.34. So 1.04 volts. Yeah. Yes, thanks. All right, any other questions? Okay. I will see you next time. We'll talk about the H bridge, which is another circuit you use with the motors. So, see you guys on Tuesday.